We use numbers a lot in our day-to-day life. They are useful for counting objects, keeping track of money and debt, describing physical systems and the way they interact, and overall they're just a very useful thing. However, we seldom think about what they are. If you ask a layman what is a number or what is the definition of a number, they'll probably say something like, a number is something that counts things. But that's not really a definition. It doesn't tell you how they behave or what they are. If you ask a mathematician, they will probably not give you a proper definition either, but for a different reason. Ask, what are numbers? And the reply will be, which ones? There are many objects we refer to as numbers. Real numbers, whole numbers, rational numbers, complex numbers. Of course, if you ask about a specific type, you might be given a definition such as the set of real numbers is the unique complete ordered field, or the set of integers is the free group in one generator. And these are much better definitions, because you can actually prove stuff with them, and they do encapsulate what these specific objects are about. But they're still unsatisfying in that you aren't being given a specific set and told, these are the rational numbers. The purpose of this series is to construct a few sets of numbers from nothing but elementary set theory. Of course, the viewer might then ask, what is a set? And I can do no more than shrug and point you to the Wikipedia page on Zermelo-Fraenkel axioms. Set theory also suffers from the problem of saying how things, in this case sets, behave rather than what they are, but it is a necessary evil. Some concepts just have to be left unconstructed so that they can in turn be used to construct everything else. One of the most well-known ways to define the natural numbers is through the so-called piano axioms. They go as follows. We postulate the existence of a set n, at least one element 0 in the set, and a function s, which we will call successor, defined on n such that s is an injective function from n to n. There does not exist an n such that s of n equals 0, and if a is a subset of n such that 0 is an a, and for every n in a we have s of n is also an a, then a must be the entirety of n. As it turns out, these are the three essential properties that natural numbers have. This is a definition in the sense that it does describe the natural numbers and all their essential properties, but it does not actually show us that they do exist. In this video, we will construct a set that satisfies these properties. In other words, a model of the piano axioms. In another video, we shall show that such a set is in some sense unique. That is, any two sets satisfying these three properties are in essence the same set, just with the numbers relabeled. Intuitively, we could construct our set n as a set of sets, where the number n corresponds to the expression on screen. In other words, a natural number is a set containing a set containing a set, and so on, and the natural number being represented corresponds to the number of nesting levels we have made. Note that the description we gave is not quite a definition. We can make an attempt to formalize it using a symbol like this one, but that is already presupposing a notion of natural number, in that we are assuming we know what we mean by repeat the brackets n times. We will then take an approach that is seen in many places in mathematics, which is an appeal to minimality. First of all, we begin by defining a set A to be inductive if it contains the empty set and is closed under the operation we will call S. In our intuitive image, n definitely ought to be inductive. Furthermore, it is easy to reach the conclusion that if I is any inductive set, it will definitely contain n, and so we are led to define n as the smallest inductive set. Of course, we do have to prove that such a smallest inductive set exists. First of all, does there even exist an inductive set? The answer is yes, because we say so. Indeed, one of the axioms of Zermelo-Fraenkel set theory, the axiom of infinity, can precisely be stated as there exists an inductive set. Second, how do we know that there is a smallest one? We will build it explicitly, starting from our God-given set I. Consider the set described on screen. It is well defined by the axiom of specification from Zermelo-Fraenkel set theory, because we are taking from our set I only those elements that satisfy a certain property, namely being a member of all inductive sets that exist. Indeed, another way to word this is to say that N is the intersection of all inductive sets. It then becomes clear that, if A is any inductive set, N is contained in A. Therefore, in the sense of some sets being subsets of others, N is smaller than all other inductive sets. We do need to check, however, that N itself is inductive. This is a routine proof, which the viewer may do by themselves, or they may just look at the proof on screen. We are now ready to define our model of the piano axioms. Our set will be N, the zero will be the empty set, and the successor function will be S of N equals the set containing N. We do need to check that three axioms hold true. Axiom 1 is a simple consequence of the inductiveness of N and the principle that two sets are equal if and only if they contain the same elements. Indeed, if N is in N, then, since N is inductive, S of N is also in N. To show injectiveness, suppose M and N are two elements of N such that S of M equals S of N. Then, the set containing M and the set containing N are equal, which means they contain the same elements. Each of them contains only one element, M and N respectively, and so M and N must be equal. Axiom 2 comes from the definition of the empty set. Indeed, we wish to show that there exists no N such that S of N equals 0. In other words, such that the set containing N is the empty set. This is obviously true because the set containing N is not empty. Axiom 3 corresponds to the minimality of N. Indeed, what it says is precisely, if A is an inductive subset of N, then A equals N. This is also easy to show, as if A is inductive, as we have already seen, N is contained in A. But since by hypothesis A is contained in N, these two sets must be the same. So, we've successfully constructed a model of the piano axioms. However, we still can't do much with it. We don't even know how to add or multiply yet. So the first next step is to rectify that problem. You might be tempted to try to, for example, define addition as follows. Adding a number to 0 is that same number, and adding a number to S of M is the successor of adding that number to M. You might already know this as an inductive definition, or a definition by recurrence. However, note that we have not yet justified that such a thing can be done. Indeed, it is not inconceivable that there might not be a function satisfying these equations, or that there might be more than one. Next episode will be dedicated to rectifying this issue. Until then, you might want to put some thought into solving this on your own. See you next time.